Hi, Mrs. Jacobs here, physics teacher at Naperville North, here to do a tutorial about how to draw a free body diagram for our forces unit. So first of all, what is a free body diagram? It's a diagram that shows the forces acting on a specific object that you have chosen to be your system for the problem. The arrows, you're going to be drawing arrows, and they show the direction of the force. It's usually going to be up, down, right, or left, although forces can be angled. You will label it to tell what type of force it is, like Fg for gravity or Fn for normal. And then you will also use on-by notation that shows what two objects the force interaction is between. For example, if I have a force of gravity, I will have on a person, comma, by the earth, if this is the force of gravity acting on the person. We'll show examples of this in just a little bit. So first of all, in order to draw the correct free body diagram, you have to start with your interaction diagram. So if you haven't drawn your interaction diagrams or you need help with that, go back and watch the previous video tutorial over interaction diagrams. So the first thing you're going to do on your interaction diagram is you're going to choose the object, which is your system. Okay, and usually it'll say like, draw the free body diagram for the box or something like that. So then you know the box is your system and you're going to circle that in your interaction diagram and count the number of forces that are acting on it. You will draw that number of forces. Let me give you an example. This was our problem 1 from our interaction diagram tutorial, where we had the box, the table, and the floor. If I'm going to draw the free body diagram for the box, I'm going to circle the box and say that's my system, and I'm going to realize that there are two forces that are connected to it, Fg and Fn. So when I draw my free body diagram for my box, I'm only going to have two forces. Okay, and one will be an Fg and one will be an Fn. Step 2, start with the force of gravity. It will always be down towards the center of the earth. So let me model that. Show step 2 up here. And here, I will show for the box, I'm going to start with the force of gravity. I label it Fg on the box, comma, by the earth. Okay. Or you can just do box, comma, earth. The on and by is sort of implied. Okay, check. I've done the force of gravity between the box and the earth. Now I have the normal force on the box by the table. Okay. So step 3, I'm going to look back at my interaction diagram, and I'm going to put the normal force because that's the force that's remaining, but I need to think about its direction. And as a reminder, it's not what the box is doing, it's what the box is feeling. So the box is pushing down on the table, but the free body diagram is for what the forces that the box is feeling. So the box is feeling a push up by the table. So I'm going to have Fn up on the box by the table. Okay. Step 4. Evaluate if your diagram makes sense given what you know about the situation and if it has balanced or unbalanced forces. Okay. If this box is at rest, then this is a balanced force situation. At rest is always balanced forces. That means all the forces are going to cancel out. So what that means for this situation is that Fn is equal to Fg. They all cancel since it's a balanced force situation. And that's my step 5. Write any force equations you can for the x direction or y direction separately. So in this case, I only have vertical forces. And when I put these 2 hash marks on there, I'm saying those 2 forces are perfectly equal and they cancel. And because they're perfectly equal. In this case, they cancel out and the overall total force is 0. That's what balanced forces means, that everything cancels. Okay, we're going to follow the same steps for the table. Step 1, circle table on our interaction diagram and count the number of forces. There is 1, 2, 3 forces acting on the table. Now, a lot of people have this correct, and then they only draw 2 forces. It's important to use your interaction diagram that you drew and make it useful for your free body diagram. So there are 3 forces acting on the table. The first one I'm going to do is Fg. On the table by the earth. Okay. The next one I'm going to do is between the floor and the table. Check off Fg. I say, how is the floor pushing on the table? It is pushing it up. Fn on the table by the floor. And then last, there's one more force between the box and the table. How is the box pushing on the table? It's pushing the table down. Fn on the table by the box. Okay, so in this case, there are 3 forces. 1 is up and 2 are down. Now, is this still a balanced force situation? It is. The table's at rest. It has to be balanced. So all forces must cancel out. How can 3 forces cancel out? Because the one that is up is greater than the 2 that are down. The total up cancels out the 2 that are down together. So I'm going to write total up equals total down. I'm going to call this one Fn1 and this one Fn2, just to distinguish between them in my force equation. So the one that is up, Fn1, is equal to Fn2 plus Fg, the 2 that are down. Okay, this is still a balanced force situation. I also don't put hash marks on anything because none of these forces are perfectly equal to each other. I can't say like this one's 20 newtons and this one's 20 newtons and this one's 20 newtons, because 20 newtons up would not cancel 40 newtons down. Okay. When we get to the math later, it'll be, you know, like 50 newtons up equals 20 newtons down plus 30 newtons down. You know, the 2 that are down mathematically will add to the 1 that is up. Okay, let's move on to problem 2. We've got a box being pushed to the right at a constant velocity. I'm going to go ahead and label this. This is also a balanced forces situation. At rest is balanced forces and constant velocity is balanced forces. I only have unbalanced forces if I'm speeding up or slowing down. When I'm drawing my free body diagram for the box, I circle the box and there are 1, 2, 3, 4 forces acting on it. I'm going to start with Fg. On the box by the earth. Check. There is a force up by the floor. That's the normal force by the floor. Fn on the box by the floor. There is a force, applied force, and the hand is pushing it to the right in the picture. So then the applied force is to the right on the box by the hand. Check. The last force is friction. If the box is moving to the right, friction is working against it, acting to the left. On the box by the floor. Okay. So the floor provides the normal force up and the force of friction, which is horizontal. If this is a balanced force situation, then all forces must cancel. The only way to have that is that the 2 vertical forces are equal to each other. They cancel out. And the 2 horizontal forces are equal to each other. I'm putting a second set of hash marks to say that FF equals F applied. I never put vertical forces and horizontal forces in the same equation. I write them separately. I'm showing here in the X direction, everything cancels, and in the Y direction, everything cancels. Our last problem, we're drawing a free body diagram for a ball that is moving to the right and slowing down. Okay, this is huge. It has to have unbalanced forces if it's slowing down. I circle my ball. There are 3 forces acting on it. So I should only have 3 forces when I draw my free body diagram. Start with FG, on the ball, by the earth. The normal force is still a supporting force upwards on the ball by the grass. The grass does not push it forwards. On the ball by the grass. Okay. The frictional force, so I've done FG, I've done FN. The frictional force, if the ball is moving to the right, then the frictional force is to the left against the motion of the ball on the ball by the grass. There is no force to the right because nothing is pushing it to the right. It has velocity to the right, but that's not the same thing as a force. Okay. It was kicked to the right in the past, but at this moment, nothing is touching it. So there's no force to the right pushing it forward. In terms of force equations, I will have Fn equals Fg in the vertical direction. It is balanced in the vertical direction. In the horizontal direction, that's where it's unbalanced. There's nothing to cancel out FF. So I'm just going to say FF is unbalanced. Or you could say FF does not cancel out. Okay, and that is what is slowing down the ball. Okay, hopefully these were 3 helpful situations for you to learn how to draw a free body diagram.